And we are live. Hello, hello, hello.
Hey,
Yeah, so this is the third stream where we will answer your questions, and we will also talk about and show more good features and like awesome stuff in DaScript. And as usual, like the entire stream will be in English, but if you don't speak English, just type your question in Russian and we will try to answer it in both languages. And after this section, after the main section, there will be like a short Q&A section where you can also ask your questions. And this is the last stream where we talk about DaScript during Gaijin Jam. So yeah, feel free to ask your question. And before we start, let me duplicate that in Russian, and then we'll start. Окей, ребята, привет еще раз. Значит, это третий заключительный стрим по доскрипту в рамках Gaijin Jam. Вот, мы с Борисом тут будем рассказывать всякие прикольные штуки. Вернее, Борис будет рассказывать, а я так рядом постою. Вот, про крутые вещи в доскрипте. Вот. Будем отвечать на ваши вопросы. Если у вас есть вопросы, не стесняйтесь, задавайте. В конце основной части у нас тоже будет такая небольшая Q&A секция. Ну или если посередине будет уместно, я тоже постараюсь задать вопрос. Вот. Трансляция будет на английском. Вот. Ну, если что, мы постараемся что-то основное продублировать на русском в конце также. Okay, I think we are ready to start.
all right. Where is it? Here we go. I would like to start with blocks and lambdas. That's been the running topic of the questions recently, and I'm going to go really, really deep in detail on how it works internally and what they do and when to use one versus the other. Let's start with a super simple example. We have a function which takes something and then invokes it and passes an argument, in our case, number 2. Here we have two semi-identical calls to that invoke something. In one, we pass the block, which takes one argument and just prints whatever the value is of the local variable plus whatever the value is passed to the block. The other fun call is just about the same, but instead it uses lambda. Let's take a look first and foremost at the output. The output's identical, it's all beautiful. And then let's look at what's generated. First, the block. This is what's happening here. The block is in length. It's passed directly to invoke something. There is no block variable. There cannot be a block variable, by the way. The local variable t is inlined. And it's straight up print. Nothing happens here. The second one is quite a bit more complicated. We create a new lambda on a heap, and we initialize lambda with some couple generated functions, and then we capture variable t and initialize it. How does it work internally? This is actually a straight up DaScript code. So what happened under the hood is DaScript unrolls a lambda in the combination of a structure, which holds a lambda function itself, a finalizer, and whichever capture variables are in there. A finalizer in our case does just about nothing. The lambda function itself is straight up invoke, takes lambda, calls the invoke, and the implementation, the lambda function actually takes the captured data of the lambda as an argument. It uses the capture variable right there. And that's our print. It's the same one as right here. The implications are very, very interesting. As you can see, block has hardly any overhead. But block points directly to the stack of the frame where the block was created. For example, let's modify the example a little bit. Notice how block now refers to the variable t directly. In this case, compiler refuses to optimize t as a constant because it's been modified. And we can see that it goes straight up on the stack. Here with the lambda, the captured code is identical. So what this means is whatever variable captures, whatever variables lambda captures and exist for the purposes, like in the scope of the lambda now. In this particular case, lambda is captured by value. So we copy a variable t. It's very easy to verify. So let's do something like this. Our lambda. Then we can do there we go. In this slightly more complicated example, we can see that for the lambda, the value is printed, then incremented, then printed, then incremented. And on that same very node, the original value of t is not changed. If we do the same with the block, here we're incrementing the actual t. Right. So those are two completely independent variables. Now, what's interesting is lambda can be captured by value, but the lambda can also be captured by reference. Remember the syntax. Something like that. Forgot the syntax. Wow, that's embarrassing. Do we cap? Oh, yeah. Replace like that. The capture modes and double, right? Expecting. Okay. Let's by move. Oh yeah. And our error is when we capture by reference, we cannot do that because why? Oh, of course, it's unsafe to capture by reference, so we need this. Here we go. So what happens here is now we capture t by reference. It essentially behaves just like a block, but if we look at the implementation internally, we actually capture a pointer to t instead of the t. That's our capture. It takes an address of t. which obviously makes this whole endeavor unsafe, hence the unsafe. And when used, the value is automatically dereferenced. So basically underneath the hood, depending on the capture mode, we either go by value, we go by reference. The capture itself can be by copy or by move or by clone. Otherwise, this is very similar to just about any Lambda in any other functional language. If we capture T by reference, we essentially get a block. And that answers the question when to use block. Just about every time you need a capture by reference and can avoid leaving the frame, like leaving the captured data frame. So if all you're doing is passing the block somewhere, like in our case, invoke something function, etc., 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 use block. Blocks are way, way, way faster. So all this beautiful machinery versus that. If just looking at the amount of code executed, it's pretty straightforward that invoking a block hardly has any overhead. If you go in deep in the guts of the script interpreter, the implementation will be in simulate.h. If you look for invoke, the invocation of the block is dirt cheap. We capture the stack frame, we write it in the block variable. Block variable holds stacks, arguments, function body, and really a little bit of debugging for that's it. And the overhead is just filling the structure, filling the prologue on the stack, and calling the value directly. If you look at how the Lambda is invoked, it's actually a function call, and it's accessing the this pointer, getting it off the heap, and capturing the variables when the Lambda is created, etc., etc., etc. So we're talking about 10 times the overhead for creation and about 5% slower invocation. So when you can use blocks, use blocks. When you cannot use blocks, think about it really hard as to why you cannot use blocks and reconsider. If you absolutely cannot do it, here's your Lambda.
Yes, so like the main rule of thumb is like think about your like variable or like Lambda or block argument and capture lifetime, right? So if like you can afford to all the arguments live like within a particular stack frame, then it's better to use blocks. Otherwise, like you have to use lambdas.
All right. Next thing I'd like to talk about is generators. Generators. Here's my beautiful example, which I wrote beforehand for once. This function returns a generator. It's somewhat similar to Python generators. It has a yield operator, which is similar to return operator, only it does not terminate, does not kill the generator. It just allows it to continue. It can be inside of any structures. And what it generates, the generator is essentially a coroutine, which you can later invoke. The easiest way to invoke a coroutine is in the for loop. You source from the generator, and it outputs the next yield up until the generator returns false. Alternatively, you can check if the generator is already empty, and you can get the next value out of generator. Here's how it looks. Here we print all the values which generator can print in first output. Here we print all the values which generator can print with the pair of empty and the next instruction. Now the interesting bit here is what on earth does that script do to generate all that stuff?
Yeah, I was about to ask, like, if like, are they like real coroutines, like they contain all the registers and stack, or is it some sort of a like I enumerator stuff
Okay,
in C#?
let's take a look in the detail. The main loop is essentially the same main loop. The type of generator variable is iterator. But the interesting bit is, what do we do in count 10? So first and foremost, it's a lambda. Just like the one we've seen before, it has a lambda function, a finalize, and so on and so forth. If you look at what it captures, this is really interesting. Inside, we see the yield value and some variables for the loop. So let's take a look in detail what on earth is going on. As far as, but before that, as far as built-in each, we have it right about here. And what it does, it turns a lambda into an iterator. This can actually be done manually with an each code. All this code exists in built-in. Here we turn a range into an iterator, a string into an iterator, and lo and behold, here we turn a lambda into an iterator. And it has very specific requirements, which we check with a concept assert. But otherwise, this code can be written manually. It doesn't have, or generated via macros. You don't have to go with the script generator keyword and infrastructure. Anyhow, let's look at what's going on in the actual lambda function and implementation. So first, we see the instruction which every book on programming tells you to avoid: a goto and a label. In this particular case, it goes to the value of the lambda yield field. And there are a whole bunch of labels. If we look at the loop, or better yet, let's look at the yield of 5. Yield of 5, 5, 5, 5. What happens is we set the yield value to 5. We set the yield label, meaning next one, and then we return from the lambda. So to make the long story short, out of every yield expression, we generate a setting of the yield value. We set the label in the lambda to point where the next time the lambda will be called from, and then we return true. And return true tells our iterator that, yes, there are more values. If we return false, the iterator will stop. The rest of this machinery is how that script turns a particular type of expression into coroutine. For example, a while loop, which is a slightly better example, is turned into a combination of if and goto for the while condition, and the goto at the end to the beginning of the if and label and while condition. So to answer your question, yes, this is proper, true, honest to God coroutines. It supports just about every functionality which DaScript has. It converts into surprisingly more DaScript. No fancy interpreter support, no nothing. By the way, you can use goto labels in your normal DaScript code. If you do, I'll murder you violently, but that's another story. And yes, DaScript allows jump to the label which is indexed in a variable as opposed to fixed. So what's the big deal about the whole generator thing? The big deal is really that this is a machinery which allows you to write coroutines. So your loop can look something like, while sound is playing, yield some enum footstep. Walk to point B. While walking, yield some enum, blah, 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 blah. So essentially, you can use coroutines to program your unit functionality, game objects, game logic, you name it. Big part of the coroutine programming is you can have multiple coroutines running at the same time and split your functionality between frames without breaking the logic of execution. I'm pretty sure some sort of collection of helpers can be written to do while something yields something, maybe an async macro, async await macro, etc., etc., etc. But fundamentally, the coroutine machinery is there. Use it, abuse it. It's beautiful. It's not particularly slow. As you can see, it generates your normal DaScript code. If you ever get to ahead of time compilation, it will ahead of time compile beautifully. And the only downside is that your variables here get captured as is or as a constants or otherwise, and they don't exist on a stack frame. They exist as part of the lambda, which may or may not be something you want. Basically, your alternative is to create multiple contexts and deal with a single context as functionality for your class. But either way, however you see organizing the code, from straight up scriptives perspective, coroutines tend to be the most intuitive approach. Back in the days when Unreal had Unreal scripts, before the days of Blue Script, Unreal script was top level coroutine, which were built in the language and whatnot. And on that note, let me move to my next example.
I have a question. Like, I'm here to ask a very stupid question, but I have to ask it. Can I just call another generator inside the generator? So let's say I have a function which yields some like enum states, and I have like another generator which uses that generator. Can I do that?
Well, I'm glad you asked. I have just the example for you.
Okay.
Welcome to DaSleep functional. If you look at DaSleep functional itself, it has a collection of iterators. Some implemented as generators, like for example, map any, and take another iterator as an input. Some are implemented as straight up iterators, and so on and so forth. Let's look at a few examples. The very first one would be With a range of 100 for each element, we do a filter called isEven, and then we verify if everything is even. Let's look at what range does. Range. That thing is straight up range. A range variable 0 to 100. Now the question is what an each over range is. An each over range is an iterator. We have it built in Dust script, but if I were to write one manually, it would look something like for x in range, yield x. The reason it exists as a C++ implementation is to make the interpreter a little bit faster in this particular scenario. Now, filter. Filter is a very interesting iterator. It has a block as a parameter. It has a source as an iterator. And it goes through each element of the source. Notice how the source is captured by move. And it involves the block. Notice how the block is captured by move. And yields an output if invoke returns true. So basically, if filter function returns true, it will yield the value. If not, it will not yield the value. So essentially, this is an iterator, this is a generator which takes another iterator, which could be generator, could be lambda, could be built-in iterator, and calls it. And here we daisy chain them in a similar manner as we do in Camel, F#, and Haskell, and other functional languages. This style should look very, very familiar. And then last one is verify even. That's a very simple test. It actually sources the input, whether it's an array or iterator or anything, and makes sure that the elements are even. In a fairly ugly fashion, but okay, this code was one of the oldest ones. Anyhow, if you look at more examples, here's the same code, whether the lambda is, the filter takes a lambda, which is written with a local syntax, local function syntax, and so on and so forth. Something as complicated as an example which takes a comprehension, which is, by the way, another form of iterator. I guess I should talk a little bit about comprehensions since we're at the generator level. So let's talk about comprehensions before we move any further. Yes, we have comprehensions, and there are exactly two. First one is like this. If you use Python or any other functional languages, this should look oddly familiar. This is a shorthand notation for an array comprehension. The brackets with a square bracket and a curly bracket returns an array, but the array is defined with a for loop. The for loop specifies the source, specifies the output, and it can also specify a filter. There we go. Only even numbers, right? If you look at what exactly Dust script does with this, here we are. We invoke a block instead of a comprehension. Inside the block, we create an array. We go through our for loop. We call our filter. We push value to an array if the filter passes. And then we return that array which we just created. Nice, beautiful, straight up, use it, abuse it. It's no worse syntax than any other. It has hardly any performance penalties. Now, what happens if we use different brackets, different braces? Well, first and foremost, the print will output, let's have a clean output. Print will tell us what we have here is a lambda, an iterator, right? And that's not the way to print an iterator. The way to print an iterator is like this. Here's our output. And if we look at what exactly has happened on the script level, and behold, this should look oddly familiar. Here's our captured variable. Here's our yield. Here's our full-blown honest-to-God generator with a coroutine, which actually yields one value at a time and doesn't store intermediate array and whatnot. This should be just about identical to the code we had above, with a yield of 0 to 5, only in our case would be 0 to 10. So back to our functional example. Here are we sourcing one generator from another generator to the map function, which maps it into a third generator, which creates an array, and here we flatten it, and so on and so forth. Here's the reduce. Reduce is very interesting. Reduce gets the value, goes through each iterator. For the first one, it initializes with it. For the rest of them, it invokes the functor. It has some performance implications, meaning overhead for the loop, but for the most part, it's beautiful. Use it, abuse it. So if you want to write in this style, you can. Just be aware that there is ginormous amount of code generated underneath. Notice the for loop turned into that little beauty. But the main benefit of this whole approach is at the end of the day, you can daisy chain coroutines to your heart's content, and it's very much supported. It's very much the mainstream if you want to do functional programming, if you want your state machine to be hierarchical, if you want to have multiple level agents, competing agents, or any other functional AI model you like, it's fine. It will work. It will live on the heap. It will properly garbage collect. Just don't forget it's a lambda, so don't try to capture by clone arrays of states. Occasional unsafe is fine to make sure what you're capturing is captured by reference. Basically write it without the unsafe first, and then to save the memory, do your captures by reference or limit the data.
So like before we go any further, like what are your like advice when to use unsafe? I guess you already mentioned some stuff. So from my understanding, unsafe is the thing that allows you to do like more sophisticated optimizations, because like it doesn't affect any of the algorithms, but it allows you to save like additional captures and probably memory, avoid some unnecessary copies and stuff. But
first the intent. The rationale behind the unsafe is to reduce the scope of where to find crashes, straight up crashes. Assuming for a second that that script runtime is flawless, which it isn't, but the intent is that it is. If you experience some sort of runtime error, you are going to get an exception. It will be thrown, it can be caught, possibly processed to a limited fashion, because exceptions in the script are thrown as to got panic. They don't necessarily gonna save you memory or save your stack frames in a fair fashion and whatnot. But you're gonna get a runtime error with a pretty good indication where exactly it happened. Unsafe allows you to create situations where data can be corrupt, where you're going to experience straight up crashes and whatnot. The good news is with unsafe, you can search in your code for unsafe, and you know that it's highly likely that your crash is somewhere underneath that unsafe or related to that unsafe. So when to use it? When you can explicitly scope the unsafe behavior. Meaning, here's my lambda. I know that by code logic, there's absolutely no way something I'm capturing is going to be out of scope of that lambda. So I'm going to capture it by reference and call it unsafe. For example, here's my local reference to a local variable. And I know for sure that I really don't want overhead of accessing that local variable. So I make a local reference and I make that unsafe, as opposed to alias, as opposed to assume expression. Assume expression is evaluated. Local reference is essentially a pointer. So that's a good way to optimize. So yes, unsafe is there to make your code fast. Sometimes unsafe is there to make your code significantly easier to maintain. Unsafe is also there when you search for unsafe, meaning it crashed. Let's see what's near it, which is broken. Oh, I'm seeing the corrupt data. Where does this data come from? It should reduce your debugging time. And that's why it's there. If you have no unsafe, you should be seeing runtime errors of some sort. And that's another way to reduce your debugging time. But it's always this dance between performance and clarity and safety of the code. DAS is not designed like Rust to be 100% safe. DAS is designed like DAS to be mostly safe, unless you try really hard. And if you try really hard, yes, you probably can make even safe code iffy. Like it is possible to create a dangling pointer, for instance. Yes, there is a good chance it will be caught, but no, there is no guarantee. But usually your sources of dangling pointers will come from unsafe code, because how else would you get an address of something? Unless you're unless you are talking to your C++ code and data comes from there and changes from underneath, but then at that point you're in the land of C++ hell and all bets are loose. But at the end of the day, that should be mostly unsafe. Mostly safe. You can sprinkle unsafe here and there when you're absolutely certain that what you are creating is good, solid, conceptually accurate, and whatnot. For example, the best example I have of that endeavor is safe address macro. This is very obviously unsafe. And yet the macro is called safe address. What it does, it takes a value in a scope, and it returns a temporary pointer to it. Notice the hashtag for temporary. And it uses a safe address tag. Now, what's the purpose of the tag? We use the function annotation to make sure that when we use safe address macro, the value which we pass to it is either local or global expression, and not say a safe address of temporary or dynamic array or lambda, etc. Basically nothing on heap, nothing outside of the local scope. So yes, it is safe conceptually to create a pointer to a temporary of the local value, but it's not, or for the global value, but it's not safe to create a pointer to arbitrary data, hence the safe address macro. So that's a good example of why you would use unsafe. So once you have a pointer, temporary pointer to a local value, your code can operate just like on normal pointers, and you know for sure that your pointer is not going dangling out of scope while you're working on it. And you can use safe address instead of regular address in just about anywhere where it's safe. And life is good.
And I guess this is one of the potential places where I can get like a hard crash even in a save mode, because I could like move or copy this pointer address to some another variable and therefore get a dynamic pointer.
Actually, no.
No.
One of the few concepts in Descript is which are like true honest to God new, is temporary values. And temporary value cannot be copied outside of a scope where it's used.
Oh.
You cannot copy temporary pointer, you cannot move temporary pointer, or not just temporary pointer, any temporary value. Temporary rates are locked, temporary maps are locked, and without the unsafe keyword, it is impossible to get the temporary value outside of a scope it's passed to. So no, if you want to write a whole bunch of true honest to God safe code which sits on pointers, use temporary.
Okay, that makes sense. Yeah.
It's fairly extensively documented in the documentation. It shows how to use it, how to abuse it, what it does, and so on and so forth. Please take a look at that at your spare time. It's one of the good ways to program on Descript that would make fairly good Descript code. By default, C++ functions, when you map them to Descript, accept temporary values, so you don't have to do much out of your code. There is a bunch of supporting infrastructure like implicit keyword, and you're allowed to specify local specialization of the functions with a temporary, and so on and so forth. Okay, let's do next example.
Yeah.
I've been asked how to profile a section of the code. In Descript proper, there is a built-in profiler. Currently, it's not yet there with DasBox, but eventually there will be. In the meantime, we have a collection of two functions, ref time ticks and get time usec. Ref time ticks gets a local time in some reference shape or form. If I remember correctly, it's in 64, which holds something platform specific. Get time usec will return you time in microseconds, on nanoseconds. I forgot the correct thing, but like I think it's in microseconds. And here I wrote a small piece of code which takes a block and prints how long the block takes. That's our same example from above. We run it. We don't care about the output. And it tells me that the first one takes 44 of those units and the bottom one takes 20. But in reality, it tells me that print is so unstable performance-wise that obviously slower section takes less. If you run it quite a few more times, you'll have slightly different values. But if you run each of them individually many times, you'll have a pretty good idea on how long each section takes. So I would have some sort of profile section option in your code, collect them, potentially print them once every few frames, do some sort of averaging, filtering, min, max, whatever your heart content desires. It's up to you. Typically, what you want is a minimal value and a maximum value, but what do I know? At some point, we're going to have integrated profiler in similarly to how we have integrated debugger. The functionality is more or less there in the prototyping state. It's really a matter of integrating it into a plugin. I'm not sure exactly the approach we'll take. The hardware one we have requires different compilation, not hardware. The runtime level one requires different compilation option. Macro, which will instrument just about every function with prologue and epilogue, would be something trivial to write. So once again, the opportunities are endless. In fact, you can put your profile section macro somewhere as a function annotation and do something like that.
I was about to ask like most of the, and you answered most of my question, but can I write like another option? For example, like does script already has like option log, which you can use to output what's generated? Can I write my own option, like option profile, which will insert like header and footer to each function with the profiling sections and something like that?
I don't think you can do it as an option. What you do is you create a module which installs a linter path. A linter path will go through like a linter macro, which happens after everything is said and done and verified. That particular linter macro will actually modify an AST and tells to restart the compilation. And basically just straight up require of that module will insert the header and footer in every function. If you like, I'm actually thinking this is a good example to provide custom header, custom footer. So I'm going to write an example for the next, till the next time we talk, and publish the link on the stream and, on the Telegram channel, and we can publish one in the Jam channel and whatnot.
Yeah, by the way, let me give you the link to the Telegram channel where all the discussion happens. And about profiling, another important question is, let's say I wrote like a simple header and footer functionality which modifies the AST. Is it possible to distinguish between like my own functions and generated by that script at this stage? Is it possible to distinguish? Let's say I don't want to like insert like a profiler code to like all lambdas, all finalizers, stuff like that.
I see. Function has a function, AST function, annotations. The one we're interested in is fun. AST function has a whole bunch of fields and flags and whatnot. So the one we're interested in is function flags, and and behold, here's our Lambda flag. You can check if it's a Lambda and not annotate it. Additionally, function has a module name, which it's in, so you can specify which modules exactly you want your or don't want your annotation to be applied. Basically, it's fully programmable and the entire AST is reflected, and typically there is enough information on what to do with the particular function. For example, in unsafe functions, you probably don't want to annotate and things like that. But yeah, I've never really documented AST and like to the point where every field is explained. It's a little bit in the flux. At some point it will settle, hopefully within the next 2-3 years. In the meantime, the best source of reference is the generated documentation, which at least will show you every field. Just about every one of them is fairly readable. And if you want to look in detail of what exactly it does, unfortunately, I'll have to refer you to the source code. And to the other examples. Macros are a big topic. I'm hoping one day there will be a book. My even bigger hope is somebody else will write it. It's really surprising to me, but there are a couple of people who can actually write them now pretty consistently and at good quality. But that being said, if you're writing a macro and discovered that you're stumbled, stuck, and whatnot, please see me on our Telegram channel. I'll gladly walk through you through the process and teach you how to write the script macros in exchange for writing a small tutorial on what exactly you're working on. Unless you have a deadline, of course, then I'll just help you. But yeah, macros are very special to my heart. It's the heart and soul of a Dask script. So if you're writing something macro, please leave at least some notes for future generations, because that's why lies madness.
Yeah, I think that's a fair trade-off.
Yes. Oh, I wanted to show one more thing. We are not there yet. In a sense, this is not a prime time functionality. It's been used in a Dask script plugin and it's been tested. It's about to be introduced in Dashbox. So imagine for a second you're completely stuck performance-wise. And there's absolutely no way you can make it on a single thread on the interpreted Dask script. And coroutine seems like too much of a hassle for this particular problem. It doesn't really feel like being split between multiple frames, and deadline is tomorrow. And behold, job queue. Yes, surprisingly, Dask script has job system as well as threading. No, you cannot use the same context from two different threads at the same time. It's not C++. So what happens there is the context is cloned. It goes through its normal initialization, but we can do lambda and pass it between context by reference. And that's how it looks. So we say we're going to use job queue. We create jobs with a status. We create a new job. And when this job is done, we notify the status, and then we join all the status, meaning all the jobs on the join will be finished. We have some means for the jobs to talk to each other, meaning here's a channel. Somebody can push objects in the channel. Somebody can pop objects from the channel. Notice they're temporary. So this particular one actually creates 5 jobs. from each of the job, it pushes the values, it notifies the channel. When we're done, we go through the channel from the main thread, and as values arrive, we get a notification. And as values arrive, we can sum them, and we make sure that at the end of the day, channel is empty and channel is open, and so on and so forth. It's somewhat similar to the Go channels, but they have status. And they mainly work. They haven't been extensively tested, but this is going to be the primary way for the jobs to communicate. So if you discover a bug in the channel, let me know, I will fix it. That being said, with jobs and channels, there are also threads.
Quick question before we go to threads. Like the underlying data structure under the channels, is it multiple consumers, multiple producers queue, or what?
It can be both. You can iterate from you can source from the channel. You can call the next, just like on any iterator. Basically, if you think about the channel as iterator and it's thread safe, meaning two different jobs can pull as well as push.
Okay.
So multiple consumers, multiple producers, if you really need to be there. Now, okay. There we go. That's my favorite sample of all time, the path tracer. You've all seen it, I hope. If not, take a look. And it can have several modes in which it operates, and one of them is jobs. Look, it's nice and beautiful. It uses job queue with the job status. It does a new job. Notice what's missing? Means to communicate channel. Why is that? Well, because in reality, sometimes you just want to straight up share data. And yes, you can. This is a Lambda, and Lambda can capture things by value, or it can capture things by pointer. And here we are with pointer to back buffer and pointer to total race count. And this is straight up data sharing mode. Notice the unsafe. If this thing somehow fails and draws over the bounds and whatnot, it's because of this unsafe. Note, we actually share data here. This is probably going to be your scenario. But once again, make sure that you understand the data model. Each new job creates a new context, which is a copy of the existing one, but without the copy of the data. That's why we have to pass the pointers to the data explicitly. And without the copy of the data includes the ECS. The DECS is not shared between context, and no, it's not context safe. So you're going to have a separate ECS on each context, and you do what you do with it. So if you need another job to do some heavy processing on the ECS, collect the data, do your job, move the data back to ECS. That being said, it has another mode. It's a threads mode.
Let me do like a little bit question slash clarification. By saying like that the job creates a new context, you mean like all the local variables, all the I don't know, like registers or probably stack will be copied because like this job like
no, it doesn't create the new context in the sense of fork. It creates a new context in the sense of spawn. Your main function will, like your init functions will run, your main function will not run. So basically all the global variables will be initialized as if you just started your program anew. And what you're going to end up with is the Lambda. And Lambda is the only thing which contains whatever been captured. If I remember correctly, the data captured from the Lambda will be cloned to the heap of the new context, but I can double check. It might exist on the heap of the old context still. I honestly don't remember.
Yeah, so
Doesn't
like in this example, the two unsafe pointers are considered as a global related to the current context,
No,
right?
in
So
this
no?
example, those two unsafe pointers will be captured by this lambda. They will be copied into lambda structure.
Mm-hmm. Okay.
And the new
Just
context can access them as if they're like normal pointers.
yeah. Okay.
So
Just because
essentially,
like
this code will run on a separate context entirely.
Okay. Okay.
Okay. Threads mode. That's actually simpler. Notice no job queue. And instead of new job, you have a new thread. You still use the same status notification. That's about it. The difference fundamentally is this is a new thread every time. This is when this lambda goes to a queue. Eventually, how many workers get done with whatever they are done, and one of them will pick it up. So if you absolutely cannot squeeze your functionality into a single thread, here's your new job. If you say writing some sort of pixel processing routine and one core is not enough, but four, you feel like four will do it, there you go. Gazillion AIs, particles, something you can parallelize. Yes, it's all very possible. If you look at how the script plugin operates, it creates a thread. On that thread, it does compilation. As far as I remember, there are multiple threads. I think it communicates with channels and whatnot. So this structure is, this infrastructure, this machinery is fairly robust. But that being said, use it, abuse it once it's there, if you have to, and let me know where it's broken. Otherwise, yeah, look at the path tracer sample. That one shares the data. It's possible. It's not safe, but yeah, it's possible. If you feel like you need to talk between contexts, use channel. We're probably going to introduce synchronization primitives other than channels and status. But truth be told, at the end of the day, code will likely look something like this. Here's my creation of a primitive, which creates a scope. Here's my threading primitives, which creates a lambda with whatever capture there is. And that model tends not to blow up. That model tends to be quite a bit less, how do I put it, race prone. Channels are not guaranteed that there will be no races. There are races in Go, there are races in Erlang. I am not aware of a race-free model which actually uses inter-thread communication, so use it on your own risk. Ideally, stay away from the madness. Ideally, a parallel for, by the way, a parallel for macro can be written absolutely trivially in this fashion. I think I have it somewhere in examples. But yeah, there's threading if you have to. And that's that. Yep. Do we have any more questions? Topics to discuss?
I guess not. I think we can conclude like the entire stream with the, well, most of the features that we discussed were somewhat related to optimization and debugging, probably with the exception for lambdas and blocks. So let's say I have a game written in DasScript and DasBox, and I don't use any of these features. I just use like a plain straight DasScript code, and my game runs slow. Where do I need to start in order to see what's slow and how to, like, what are the best practices that I can
As
use.
of right now, you'll need to introduce some sort of profiling facilities to figure out where is it spending time. Look at what exactly it's doing. What's it thinking? Potentially reconsider the scope of what it's doing and how it's doing it. Basically, before any of those language-specific optimizations like generators, lambdas, etc., make sure you went through your classic CS 101. Am I using n-cube algorithms instead of nlog-n? Am I running way too much data, not enough data? Is my data reasonably well organized? Am I doing something stupid? This kind of thing. And if your code is clean, if your algorithms are sane and you're true, honest to God there, your game runs, it does all you need to do, and what you're missing is, I don't know, 2-3 times the performance. The next thing to look at is, can I split some of it between the frames, and how difficult that would be? And another thing would be, is something really fits massively parallel computing mode, meaning jobs or threads. If the data is truly independent, you actually can split it in multiple contexts and use threads or jobs and whatnot and get there that way. Ideally, you can share the data. If data is read-only or write-only, and bits don't talk to each other, if it's particles, if it's pixel processing, if it's gazillion times the same thing, isolated in a small loop, things of that sort. That. Otherwise, you're in the land of creative optimizations. And your last option is, of course, to compile your own version of DOSBox and use ahead of time compilation for your game. And that will probably give you about 10 times the performance, because that's what it tend to be from interpreted to compiled. If I have to call one ballpark number, it would be that. In some cases, it would be as low as 3 times. In some cases, it can be up to 20, 30 times. It really depends on how complex your code is. But if what you're doing is, here's my straight up DAS script, which looks like Fortran with ECS or without, interpreter is about 10 times slower than ahead of time. So yeah, you can compile your own version of DOSBox, hook in ahead of time compilation. There are examples of how to hook in ahead of time compilation in the script proper, and turn it on and hope for the best. That, to be honest, would be my last resort. I'm hoping you're not writing new StarCraft 4 or something which requires massive amount of resources, so that you do need more than modern computing performance. Hopefully at some point by the end of this year, we'll turn on the JIT as a prime time option, and then that option would likely be completely unnecessary for DOSBox games. In the meantime, yeah, you get to optimize a little bit. Fun.
Yeah, and I think like the last measure could be just turn your game into a turn-based game.
I'm a big fan of turn-based games. Turn-based first-person shooter, my favorite.
Yeah. Okay, I think, yeah, we've said enough. Let me do like a quick conclusion, and then I will do the same in Russian, and then we will finish the stream. So what we discussed today is the difference between blocks and lambdas. The main difference is that the blocks is basically generated scope, and lambda is like a complete structure with its own like initialization and finalization and captures. And the main reason where to use blocks and lambdas is, think about your like variable and your capture's lifetime. If you can if you can afford them to leave it within a single scope, then probably you should be end up using blocks. Otherwise, just use lambdas. What else? We also talked about some how to use generators, and it's basically a way for you to write code that could be split into multiple frames, or just a nice way to organize like asynchronous code, or like some way to just organize the code in a, I don't know, like functional way, or just a nice way to organize the iteration itself. So that's the idea behind the generators. And we also showed how to use it in a functional fashion, like MapReduce way. And also how to write your own game logic and like finite state machines using it in like pretty much the same way you might end up using it in, you know, like other game engines such as Unity, or I don't know, like whatever it is. And we also talked about profiling and how you can do how you can make a macro which will be adding like the footer and header annotation to all necessary functions. Also talked about the generic things to measure time. And yeah, I also like did a quick introduction on the existing job system and threading. And if you want to have a look at how it works, just go and see the toy path tracer example. Yeah, I think that's the overview of today's discussion. And yeah, let me do the same in Russian. Окей, ребята, еще раз повторю. Значит, мы сегодня говорили много про тему. В основном она касается оптимизации, но не только. Это еще и фичи языка в том числе. Вот одна из таких фичей — это блоки и лямбды, и мы поговорили про их отличия. Вот. Основная идея блоков — это в том, что это, по сути, кодогенерация просто локального скопа. Вот. А лямбда — это полноценная лямбда, структура с кэпчерами, с инициализацией, финализацией. Вот. И поговорили про то, где, когда, что лучше использовать. И основная идея — это что если вы можете позволить lifetime всех ваших переменных, которые идут в capture, быть вот в рамках этого стекфрейма, то, скорее всего, вам надо использовать блок, вот, иначе это лямбда. Вот, скорее всего, это так. То есть, наверное, основное такое правило — это вот подумайте про lifetime и посмотрите, где. То есть по дефолту старайтесь использовать блок, потому что он просто быстрее. Вот, поговорили про генераторы, да, как способ в целом организовать итерацию, как способ писать асинхронный код более-менее линейно, как способ писать в функциональном стиле, тоже более-менее линейно. Вот показали примеры тоже функциональщины, показали примеры, как писать конечные автоматы. Вот, просто показали, как писать разные итераторы. Вот, поговорили про профайлинг, поговорили про макросы, как можно в теории и, скажем, на практике тоже написать макрос для того же профайлера, который будет все функции оборачивать, да, и показывать время всего, что есть в проекте. Вот. Поговорили в целом про какие-то базовые советы оптимизации, да, и поговорили вкратце про текущую джоб-систему и про треды. Вот. Все это есть в примере той path tracer, можете глянуть. Вот там можно как раз увидеть все. Фух. Yeah, I think I finished my conclusion. Do you have anything to add, Boris?
Not really. We have more stories, maybe one day.
Yeah.
But this is a good amount of data for today.
Yeah, I think so. Yeah. Mm-hmm. And for those of you who are participating in Gaijin Jam, I think you have like one week left. So yeah, I think maybe it's a good time to start thinking about your game performance, about how to like finish it and how to make an actual build and how to profile stuff. So I think it might be valuable for you. So yeah, feel free to like watch it again and use all the techniques that we shown here. Yeah, I think that's it for today. Yeah. Thank you, and we will see you sometime in the future. Okay, bye.